Good afternoon, everyone. We're Team 18, Grid Free. My name is Justin. This is Alex, Gal, Emily, and Dawit, and our project is a portable solar energy harvester. So, project overview. The idea behind our project came from our client, Albert Crooker, who is a recent BU alum from the College of Engineering. After meeting with him, we decided that the objective of our project is to design a portable, power-optimizing solar energy system. The two main components that we have are the portable harvester unit as well as a base charging station. On the actual harvester, it's able to record GPS and power data as well as charge a LiPo battery. And on the base charging station, it's able to use the energy that we charge the battery with to power consumer electronic devices. And also we process the data that we record in order to recommend optimal placement for the harvester. So the overall significance is to provide a convenient and inexpensive way for a consumer to harvest solar energy and use it without tying the energy to the grid, hence our team name Grid Free. Some accomplishments that we've made throughout the year in terms of system functionality, we were able to collect and store solar energy into a battery. From the battery, we were able to charge consumer electronic devices at both 5 volts and 12 volts. And then we're also able to transfer data between the solar harvester and the base station. Some design milestones. We're able to implement a user interface both on the harvester and the base station. We constructed customized designs that Dawit made for the solar harvester and the base station. And then the main thing throughout the project we needed to make sure was that our energy collected was greater than the energy that we used within the project, which we did. We were energy positive. And a little future work that would have to be done. Due to some initial design choices, we had some trouble interfacing between with the real power data flow due to software issues. And the harvester is currently a prototype due to non-weatherproofing.
Hi, so I'm Alex. And this is a basic technical overview of our product. So it all kind of starts with the solar energy, which is collected by a photovoltaic panel. It's a polycrystalline panel, and that energy feeds into the charging circuitry, which consists of a boost converter, a bunch of measuring circuits, and the battery charge controller. The power feeds into the battery, which is a LiPo battery, which I'll explain later, and it's all controlled by an MSP430 as the central processing unit. So that controls the LCD user interface, as well as reads and writes data to the SD card, and it also obtains data from the GPS. Also on the harvester side is the mounting mechanism, which allows this panel to be mounted to a few different surfaces, and waterproof design, which would be a topic of future exploration. So the batteries move to the base charging station, where the charging station can be entirely charged from the battery. So that is fed to a DC to DC regulator system, which is also optionally switched with mains voltage in order to allow the user to charge things if the battery is being charged by the panel currently. So that DC to DC regulator system feeds to a 5-volt USB charger and a 12-volt charger for consumer electronic devices, and also powers a Raspberry Pi, which is the high-level microprocessing unit of the base charging station, which the Raspberry Pi interfaces with an MSP430 in order to communicate with the SD card, and also controls the LCD user interface directly. So my part was specifically to measure, regulate, and transport energy from the sun into the battery bank, into the battery, which starts kind of with the custom-built solar panel. It's 2 feet by 1.5 feet, outputting around 10.5 volts and 3.6 amps at peak production, which is around between 35 and 40 watts peak production. It's also the power conversion circuitry, which includes a boost converter in order to change the voltage to the battery charger input level, and also a linear regulator to power the processor, the SD card, and the GPS chip. Also, the battery and the charger were my part, and the battery charger regulates the voltage and current going to the battery, because a lithium polymer battery requires very specific charge cycle in order to charge without breaking it. And we chose a lithium polymer battery because of its high energy density, and it's 11.1 volts and 6,400 milliamp hours. Also, my part was the measurement circuitry, which was to track voltage and current throughout the circuit in order to regulate the power flow and also to take data about that. There were some issues that arose at the end with measuring current, namely that the current was oscillating and it made it difficult to measure. So that is would be a topic of future editions.
So I'm Emily, and I worked on the data flow in our system. So that includes the collection, transfer, and storage of data on the system. Data enters our system through the GPS, collected at the GPS module. It comes in as a raw data form in an MEA protocol. So we parse that data and we decode it into variables that we can use. This data, along with power data that we get from Alex's circuit, is periodically logged onto an SD card. We do that by having a timer and logging in like every 1 second. We put on information onto the SD card. This is done through a SPI interface using the SD protocol. Our SD card is set up so that we have a status block that consistently updates the status of the whether the SD is coming from the Raspberry Pi or is it coming from the harvester. So it tells us what's the status of the SD, and then all the rest of the blocks are used for data. So that's how that's sectioned off. This data is also displayed in live time on a 2x16 character LCD display, and the information is eventually transferred over to the Raspberry Pi to be processed. Minkal's next.
Hi, my name is Gaukhar, and I'm responsible for power utilization on the base station as well as the PCB design and schematics. So base station has two main outputs, which is 5 volt and 12 volt. We also use a LiPo battery that we transfer from the harvester to use. We use it as a main input power. For 5 volt outputs, we use a buck converter. We can charge USB devices at 5 volts, and for 12 volt output, we implemented a buck boost converter to be able to charge at 12 volt. So I also implemented an alternative feature to be able to charge the devices from the wall outlet in case we are not able to charge the battery if there is no sun outside, or maybe the battery is discharged and we really need to charge the devices. So we use a switch to change the modes of operation from the input power from the battery to the input power from the wall outlet. And for the PCB, we decided not to use the PCB due to some technical issues, and we use a prototype board instead of that. That's it for my part.
Once again, I'm Justin, and my lead was the user interface on the base charging station. We chose to use a Raspberry Pi as the main processor on the base station. This interface with a 20x4 character display, as well as 3 push buttons for the user to interact with the data. We also had, in order to check that the information we're getting is correct, we have installation data stored on the Raspberry Pi. This we gathered, it was documented by NASA. They had a 10-year average of the specific solar radiation per location per day. And then we were also able to obtain an RSS feed through Yahoo Weather to get the current weather data as well as the weather forecast for the next few days. This is all used to suggest the optimal placement, where it'll take the list of locations that the harvester has been placed and then rank them with the best location at the top.
Hello, my name is Dawit. I am the mechanical lead for this project. The solar harvester and base station units were both mechanically designed using aluminum sheet metal. The base station was used using 1/16 inch aluminum sheet metal. It was precision cut with a sliding battery access panel, charging ports, including USB ports, switches, and everything for the LCD, including the buttons that it would use. The solar harvester enclosure was going to be used more outdoors to withstand the corrosion of the outdoor weathering system, but we weren't able to make it waterproof completely. We had custom built all the enclosures internally using the new Epic Lab, and we used CAD to design and the plans, and then from there we measured and made all the cuts in all the drill holes and everything and so forth. One thing for the solar harvester we did was that we provided multiple mounting systems for that, One was to have it to be able to be mounted on small angled surfaces, such as like a small, like a shed. So we had rubber tracks for that, and another one was a ground mount that the user can manually adjust the zenithal angle to be able to capture the most direct sunlight. And the last thing was a car roof rack mounting accessory that is extra.
So we have a video for you guys.
So, in conclusion, our reliance on fossil fuels is causing climate change and environmental degradation. Solutions require that customers opt for green energy sources wherever possible. And as such, it's necessary that these sources be made more available to them, including options where the source does not have to be connected to the electrical grid. It is for that reason our portable solar energy harvester serves this need. Providing the consumer with a convenient, user-friendly means of directly charging their electronic devices without using solar energy, all with an efficient system that is grid-free. We'd like to give a special thanks to Professors Pisano and Professor Kia, Professor Hornstein, Professor Giles, Professor Klepson, the EPIC Lab, and our customer Albert, and a special thanks to our entire BU ECE Class of 2014 family. Any questions? How much does that weigh?
It weighs roughly, say, 10 to 12 pounds. For the solar harvester, that is.
This prototype ended up costing, I think, $150. But that was because we didn't use a lot of optimized, like for example, we used a commercial battery charger rather than a charge controller IC. So the cost would be reduced down to probably around, this is an educated guess, but around $75. And the biggest cost is the battery, because the battery itself costs $65. So if you either buy them in bulk or discount the price of the battery, because assuming that it's expandable, then that.
What's the current in the 5-volt outlet?
Provides 2 amps at 5 volts.
What happens if I try to draw more?
I have a fuse that protects the electronic devices, and it tries to draw more current, and it just falls.
So a traditional fuse that would need to be replaced?
Yes, I did not implement the resettable fuse. It is a yeah.
What is the weight of it?
12 pounds roughly.
For the solar harvester, for the base station unit, it's a little more than that. I'd say it's about 14 pounds.
But the solar harvester is what's made to be portable.
Yeah, the base station would be indoors, used indoors as a centralized unit to transfer the battery and charge your small electronics.
And that was kind of a toss-up we had to make, where it had to be portable, but also had to be heavy enough that it would counteract, wind and things like that. Because it has to be portable means it can't be mounted, which means it has to be heavy enough not to be blown over or blown away. So it was balancing it.
Are you aware of the fact that there are some flexible solar panels?
Yes, that I mean, we had talked about that in the beginning, but the cost would be driven up by that, because as far as I know, I mean, and they are more efficient, but in this case, intending to be a cheap consumer electronic device, or consumer, I guess, energy producing device, that's not a path we wanted to go.
One more question.
And Professor was really good too. Go ahead.
You said it was net energy positive.
Yes.
So what was the maximum amount of power that you can get out of it, subtracting off what total energy is used up?
Well, okay, so at max production, which is the rating that's given by the solar manufacturer, which is very, very rare instance, it was around 35 watts from the panel, and the power electronic circuitry is about 50 to 60% efficient, again, depending on a couple of factors. So we didn't end up taking measurement because it relied on a lot of different factors, but in our testing, we extracted energy, well, we harvested energy, and that entire system is standalone, so we delivered net energy to the battery, and then the battery powered the base station, the Raspberry Pi, the LCD, and the actually charged devices. So I can't put a number on it because it depends on a lot of factors.
Thank you.